Welcome to a lesson with Dr. Powell. This video is a continuation of the last few where we're looking for invariant subspaces of R3 with respect to the action of a matrix and polynomial scalars where X represents the action of the matrix. Okay, so we've worked through some steps and we've gone through some notes. And now we're on step 4. Now we're ready to actually find a subspace of R3. And what we're going to do is we're going to look at the different basis vectors that we had for Rx3, right? For Rx3, so P1, P2, and P3. And we're going to look at the ones that didn't actually themselves mod out to 0. So we're going to look at those ones. And each one of those is actually going to give us an invariant subspace. So we're going to be looking at 2 invariant subspaces here. One associated with this P1, one associated with P3. Now, along the way, we're thinking about ABC coordinates. So here in the slides, C refers to the last guy, P3, and A will refer to the first one, P1. So we're going to get 2. Now, notice when we modded out, we actually had something that was isomorphic to R. And over here, something that was isomorphic to R2. That is when we assume that these guys right here were 0 with those multiples. Well, what this is isomorphic to R and what this is isomorphic to R2, actually, the invariant subspaces in particular that we are looking for. And so we just have to see exactly what vectors they are as in R3, what maybe a basis is of this R2, this dimension 2 subspace, and what a basis is of this dimension 1 subspace. That's really what we're doing here. So we're pretty much about there. Okay, so in particular, let's look at the last guy right here. So where P3 would take us, or the coordinate C. All right, so we know that in this coordinate, what is the action of A? Because remember what all these things are. These are like the columns of A, right? So in this coordinate, all right, in the last coordinate right here, this is 0, meaning that x squared minus 2x plus 1, if we multiply it in the last coordinate, it's going to be like 0, multiples of it. So that means that the minimal polynomial that of the action of A, which is, with an x, that would actually make 0, like the smallest guy that would actually do that, is that multiplier, x squared minus 2x plus 1, because that represents the action of A, which is 0 there. Okay, so that's how A is acting, right? A acts nicely, and if it acts this way in that polynomial, that's going to be 0. Okay. So what we're going to be looking at is the Rx span of P3. P3 was this. What is the Rx span of P3? Well, it's going to be like P3 and then multiply x to P3, multiply x squared to P3, and take all R linear combinations of those if we want to think about R linear combinations, right? Except for when you have x squared, you can do a little division, look at a remainder, and the remainder is going to be degree 1. So you're going to be back into here. So really what we need is just the R span. So multiples of real numbers, linear combinations where the scalars are real numbers of these two guys. That's really all you need. And that is the subspace, the dimension 2 subspace that's associated with that P3 vector. So, now so we know what that is in R3. What's this? Well, it's just X acting on that. So let's just do it. What does this do? That picks out the middle column, which is 0, 0, 1. Right there, that is the subspace. That is invariant under the action of our matrix. Okay, that's associated with that P1 right there. Okay, what about the next one? The one-dimensional subspace corresponding to the first guy, P1 here, or first coordinate A. It's just the Rx span of this guy. But remembering in this component, the minimal polynomial is x minus 1. So when we do a little division here, look at remainders that have degree 0. So we're just looking at constants, right? So we really just need R multiples of this. Like in the last one, we needed just, we went this far because the minimal polynomial was this. And so dividing by this gave you degree 1 stuff. And so you have dimension 2, you just did this and then an x times it. And if you kept going, if it was like a cubic, you do like, you go up to x squared. So it'd be this x times that and then x squared times it, but it's of the same thing every time. But actually that gives you things that are linearly independent in R, um, for R span. So it gives you dimension 2, which is kind of nice. All right. So here, the one-dimensional, so basically we just look for R multiples of this. So that is the subspace with that as a basis. And that fills up all of our 3. So we just have identified, this is a fairly simple example of a matrix that I used, but we're able to focus on kind of the process and what actually happens here. And we're able to find our subspaces. So that's one right there. In that case, so this is the subspaces we found, the one from P3, the one from P1. These are called the invariant subspaces. And I would correct this to say of R3 with respect to the action of A. Okay, the minimal polynomial of A, actually, so let's have a little discussion of that just for a second, is actually going to be equal to the least common multiple of all of the minimal polynomials of all those invariant subspaces that we saw. So from P3, the invariant polynomial was this guy, and from P1, it was this guy right here. The least common multiple of those two is this right here, x squared minus 2x plus 1. So that's actually the minimal polynomial of A on all of our 3. This will be equal to the zero matrix on all of our 3. But it wasn't the minimal one on all of it. There was a whole subspace where x minus 1 was enough to be the minimal part. Okay, so this kind of helps us think about minimal polynomials, and invariant subspaces. The least common multiple of those is the minimal polynomial overall. We're going to be using some these ideas as we move forward. It gives us some intuition to enable us to actually compute things called eigenvectors and values and other things like that rather quickly, if we have kind of a nice sense and feel for what we're doing here in this case in looking for invariant subspaces. Those things will help us diagonalize matrices and do other things as well. Thanks for watching.